Keshav Dasgupta, who's usually at McGill University, although today he's coming from California, so we can't blame him for the bad weather. And he's going to tell us about how hard it is to get de Sitter solutions from string theory.
Very hard.
Thank you very much for inviting me. Such a nice department. So, title of my talk is how hard it is to get de Sitter solution from string theory. You may probably know many of the details, but just we analyze some of these things in a more modern light and try to argue how, under what condition you can get a de Sitter solution or a KKLT type of solution in string theory. So, as I said, I will summarize some of my older works and some new works that I have started on the subject, and will be based on the following papers. The one which just came up last year, it's called De Sitter Backpoint Type 2B String Theory, Classical Solutions and Quantum Corrections, done in collaboration with these set of collaborators, and the paper that I am finishing right now with Eric Keshav, Renata, Antoine Van Proyen, and Tim Res. So this should come out soon. So here are the cast of characters. This is Rhiannon, my first student, who is now a postdoc. Mohammad Mia, my second student, and he unfortunately got a great job in New York, so he's leaving physics. It's too bad. Evan is my student whom I'm sharing with Robert Brandenburger. And Radu Tata, my old collaborator with whom I have written quite a few papers. And now here is Eric Keshav, you probably know him very well. Renata Kalosh, you know her. Antoine Van Proyen, and Tim Res. Tim Res was at Stanford, son. He just left for Vienna. So the outline of the talk will be a brief introduction to a no-go theorem. Then I'll discuss the no-go theorem in the presence of fluxes. Discuss the no-go theorem in the presence of branes and anti-branes, in the presence of orientifold planes, and I'll discuss the possibilities of getting a 4-dimensional de Sitter solution with higher order quantum corrections. And finally, I'll end with some discussion and conclusion. Well, as you know, it all started with the work of this gentleman, William de Sitter, and followed by the joint work of two physicists, which led to our modern understanding of the accelerating universe as a 4-dimensional space-time with positive cosmological constant. Now, question is that since string theory is supposed to explain everything of nature, is it possible to get a positive cosmological solution in string theory in 4 dimension? Now, I'll not talk about it, but as you know, it's very easy to show that lambda equal to 0 and lambda less than 0 solutions are abundant in string theory. It's not too hard to get those solutions in string theory. Now, one of the reasons is that these solutions tend to lead to supersymmetric backward. So, when we ask for lambda greater than 0 solution, we are typically asking for solutions for a background which are non-supersymmetric. It's not known in general a positive cosmological solution to have a supersymmetric background. By definition, it cannot have. So, although lambda less than 0 solution can have supersymmetric and non-supersymmetric, because there could be non-supersymmetric ADS solution, but generally they are always non-supersymmetric de Sitter solution. It turns out that that solution is rather hard to construct, but this is not the only reason. There exists a much deeper reason why in 4 dimension de Sitter may be difficult to construct in string theory. will argue in this talk that if the gravitational theory has only two derivatives, then it may be impossible to construct a four-dimensional de Sitter solution in that theory. Now, why is this the case? And I'll explain to you in very easy steps, and I'm sure many of you know all of these things in details. So, let us consider the following action. Just for simplicity in d dimension, I have an Einstein term and a matter Lagrangian, where k is the Newton constant, Rd is the Ricci scalar, Gd is the determinant, and L matter could be anything. I couple this thing to Einstein gravity. It can contain global fluxes, it can contain scalar fields, it can contain local sources. Now, if you vary this action with respect to the metric, you'll get this simple relationship in which the curvature is connected to the energy momentum tensor, where T is the energy momentum tensor and T is the trace defined in this particular way. Now, let us consider for simplicity a metric of this particular form. So, it is a four-dimensional metric, and then there is some kind of internal metric, and we'll demand that this four-dimensional metric, well, of course we have split the geometry in this particular way. So, and the condition on the M this internal space could be compact or non-compact. It doesn't matter for this. And the key quantity you want to study is the Ricci four-dimensional Ricci scalar. So the claim is that if R4 is greater than 0, we obtain a positive curvature solution, which leads to a de Sitter space. If R4 is less than 0, we get an anti-de Sitter type solution in four dimension. So the condition for which we require to get a positive curvature solution boils down to this particular thing, which means if D is 10 dimension, the relation is very simple. The trace of the energy momentum tensor in four dimension has to be greater than the trace of the energy momentum tensor in the internal dimension. If we satisfy this, you will get a four-dimensional de Sitter solution. That's all is required. Such a simple condition. And one might think that with such simple condition, it's very easy to construct a solution or a background in which the trace of the energy momentum tensor in four dimension is greater than the trace of the energy momentum tensor in the internal direction. So we'll ask this question in a two derivative gravity. Is it possible to satisfy this particular criteria? So to test, let us take a few examples in string theory and ask whether we can satisfy this particular condition. Now, the previous work on this aspect was done by Maldacena and Nunes, where they analyzed the presence of fluxes and branes, but they did not analyze the presence of anti-branes or orientifold planes or anything like that. And there was a law at some point that the anti-branes can be used to uplift anti-de Sitter solution to de Sitter. We see that this is not the case. It's impossible for a brane or an anti-brane to uplift. Anti-brane can break supersymmetry, but it is not possible that anti-brane can give you a positive cosmological solution. It breaks supersymmetry but will not give a positive cosmological solution. For example, if you put an anti-brane in a DS space, it will not give you a de Sitter space. It will give you a non-supersymmetric anti-de Sitter space. So let's see how this pans out. So first let me introduce, of course, the string theory, and many of you probably know what is string theory, and I'll just give a small introduction to string theory. The rest of the details you can read from the books by Melanie and Catherine. Now, string theory by definition is an interesting conjecture for renormalization to flow, where an infinite tower or new massive degrees of freedom appear at certain high energy scales. So this is actually a definition of string theory. String theory is a theory in which new degrees of freedom appears at a certain high energy scale. Being massive, they are all integrated out at low energy and therefore do not change the infrared physics. The infrared physics is therefore captured by the supergravity Lagrangian. The new degrees of freedom enter the gravity loops to allow for an ultraviolet completion of gravity. This is almost like, as you probably know, like the massive W plus minus degrees of freedom that enter the four fermion interaction to allow a good ultraviolet behavior in the Weinberg-Salon model. So what string theory does is that it just enters the loops of the Einstein gravity and renormalizes the Einstein gravity at very high energy. So it's a UV completion. But compared to field theory, there are, as you know, there are no free parameters in string theory, and string coupling is determined by the expectation value of the relator field. In addition to supergravity fluxes, string theory has extended object called branes and orientable planes. It turns out there are massless fluctuation of these objects that could change the infrared physics, and therefore these degrees of freedom should appear simultaneously with the supergravity degrees of freedom for specific choice of string coupling. So string theory is by definition a theory in which the massive degrees of freedom have been integrated out to express the theory as a supergravity theory, and then there are extra massless degrees of freedom coming from these extended object in your theory, which affects the infrared physics. There are 5 well-known theories, but today we'll only concentrate on a theory called the type 2 string theory. Now let's see what happens in the presence of fluxes. So this is well known, but this is the analysis which Maldacena and Nunes did a few years ago. So the matter Lagrangian, I'll write it like this, where F is some antisymmetric object. And this is how the Lagrangian of the fluxes appear. And all you have to do is to compute the energy momentum tensor of this, and it's an easy exercise. You just plug in every value, and you'll get an energy momentum tensor which looks like that. So now what is the constraint to get a de Sitter solution? The constraint is that the trace of the energy momentum tensor in 4 dimension should be greater than the trace of the energy momentum tensor in the internal direction. And you plug this in and you'll get this relation which looks like that. So you might think this relation is very easy to satisfy, where Q is the form, how many indices are there, this determines Q, F square is the square of that. If this is satisfied, then of course a positive curvature solution can be satisfied with fluxes. So question is that, is this inequality ever satisfied?
Excuse me? What was the index 8?
These are the form indices, A1, A2, A3.
So it's like small m, but...
For type 2B theory, you know that there are 3 form and this form, so A1, A2, A3 can take 3 form or 1
Yeah,
form.
just in relation to this capital M and mu.
Where is capital M?
This capital M and
Oh, okay, so this M and N is the total space-time 10 dimension, and A1, A2, A3 are the fluxes
yes.
in the internal space. So you get a relation which looks like that. So everybody thought this relation can be very easily satisfied. The first person to show that this relation can never be satisfied in string theory is Maldacena and Nunes. And why is this the case? You know that when I write it in this particular way, this quantity is always 0 because mu is the space-time direction and A1, A2, A3 are the fluxes in the internal space. So if I put all the fluxes in the internal space, then this quantity is 0 because there are no legs along the space-time direction, so this is 0. F square is a positive definite quantity. Q is greater than 1, this relationship can never be satisfied. You can easily see. Now, why can't I have one F along the space-time direction? The reason is that I'm looking for maximally supersymmetric de Sitter solution. So if I put one leg of the fluxes along the space-time direction, break the symmetry of the theory. So I don't allow this kind of fluxes. Therefore, this relationship in the presence of internal fluxes will not be satisfied. So this is exactly what I said over here. Now imagine you take Q greater than 4, you take a very big fluxes in which you can put all the 4 legs of the fluxes along the space-time and the rest along the internal direction. Question is, under that condition, can this relationship be satisfied? And you plug everything over here, you find that this inequality can only be satisfied if Q is greater than 9. Then you can put 4 legs of the fluxes along the space-time and rest along the line, which means that you require a 10-form fluxes in string theory, but there are no 10-form fluxes in string theory, so you cannot satisfy. So how that relationship was so simple, but as you see, no matter how much fluxes you pump in the theory, you will never ever be able to get a positive cosmological solution in string theory. This is the celebrated Malasena universe.
Assuming supersymmetry.
Huh?
Assuming supersymmetry.
Assuming maximally symmetric theory.
That's a big assumption.
That's a big assumption, but if you break that, then that's a different issue altogether. All right, so but this is all is not lost because we have D-brane and anti-D-brane in string theories. So the question is that can they be used to do uplift? So this is something good. Yes, such combination of object can surely give a 4-dimensional response. The question is, can they give? So I will take a D-brane, and to this audience I don't have to explain what D-brane is. D-branes are objects in which open string can end, and as you know, all these interaction like this can happen for a D-brane. Closed string can come out and interact with an open string, and they give rise to this interesting phenomenon. Now, it turns out that the D-brane action, if you write it, it has 2 pieces. It has a piece called the Born-Infeld piece, and another is a piece called Chern-Simons. And if you normalize everything properly, the Born-Infeld piece comes with a minus sign, and the Chern-Simons piece comes with a coefficient mu p in front of it. C is the Ramond field, and e to the power of f is the piece associated with each field and all. So question is, these are basically the definitions of so-called pullbacks, and it turns out that if we know that Tp is the tension is greater than 0, and the sign of mu p determines whether you have a brane or an anti-brane. So D brane is defined by a term like that with a positive sign over here, and anti-brane is defined like a term like that with a negative sign over here. That's the only difference, at least at the level of supergravity solution. Now, what is the Chern-Simons piece? The Chern-Simons piece is, as you know, by definition, is independent of the metric, and therefore there are no contribution to the energy momentum tensor for the Chern-Simons piece. That means the energy momentum tensor that you can compute from the Chern-Simons piece has to be 0. Now, since, as I said, mu times L Chern-Simons is the only way to distinguish a brane from an anti-brane, this term does not contribute, and therefore the brane on an anti-brane will contribute equally. So if the brane cannot be used to uplift a anti-de Sitter space to a de Sitter, then anti-brane cannot be used to uplift an anti-de Sitter to a de Sitter solution. So now just consider the Born-Infeld piece. And for the Born-Infeld piece, I can easily compute the trace of the energy momentum tensor for a dp or an anti-dp. And the result is given in terms of like that. And I can compute the trace of the energy momentum tensor in the internal space given by that, where the quantity alpha is this one, Tp is the tension of the brain. And now you can easily see, since alpha is positive definite, energy, the tension of the brain is positive definite. If you take P1, 3, 5 and 7, you cannot satisfy this relationship. So energy momentum tensor in the space-time direction cannot be bigger than the energy momentum tensor in the internal space of any brain starting 1, 3, 5 and 7. The only possible way it can happen is 9 brain, but then 9 brain cannot exist in type 2B theory. Type 2B theory doesn't have 9 brains. To put 9 brains, you need to cancel the charge of a 9 brains. You need to put an oriented for 9 brain. This way you cancel it out, and you'll actually not be able to get a 4-dimensional de Sitter space. So the conclusion is that neither the brain nor the antebrain can create enough energy momentum tensor to give us a 4-dimensional de Sitter space. So question is, could P equal to 9 help? It turns out that it does not, because of the certain something called the global charge cancellation in the theory. So that sad and it failed. Now you might worry about the fermionic piece on the brain or an anti-brain. Question is that can the fermionic pieces of the brain or an anti-brain can conspire to give us the cosmological constant, positive cosmological constant. So this is the work that I am doing with Renata and other people. It turns out that the fermionic terms on a brain or an anti-brain, it can be understood simply by replacing the bosonic terms of the Born-Infeld and Chern-Simons action by their fermionic completions. Let me give you an example. How does the fermionic term look like? You take the bosonic piece, C phi is the scalar, C0 is the axion, B is the NS field, G is the metric, C2 is the Ramon-Ramon field, and C4 is the four-form field. To add a fermionic piece, all you have to do is to redefine all the field by certain thing called fermionic completion. The scalar field, the dilaton, is defined as a new fermionic dilaton which contains the scalar field plus the fermionic. Similarly, the axion is defined like that. Now this delta 1, this one I wrote it in a symbolic way. This could contain an infinite series in theta theta bar. That could contain very big series. This is the NS field written in terms of an antisymmetric tensor, which is a fermionic variable. Similarly, this is written in terms of a symmetric tensor, and so on.
So are you imagining a situation where you've got some fermionic condensate or something?
Yeah.
So these guys actually have.
That's right. It's maps. Yeah, these guys are. Now all you do is that take this whole stuff over here and plug it in the Born-Infeld action and the Chern-Simons action. Just plug these fields back, and you'll get your fermionic. And as I said, they are in some series in delta delta. Once we plug this in the Born-Infeld plus Chern-Simons, we'll get the full fermionic action for the brain or the anti-brain. So the fermionic terms should just be assumed as certain symmetric or antisymmetric terms added to the symmetric or antisymmetric bosonic fields of the theory. But just now I showed that since either symmetric or antisymmetric fluxes cannot uplift, the fermionic terms cannot be used to uplift a de Sitter vector because we are taking exactly a symmetric or antisymmetric combination. Now the fermionic terms, however, have other uses that we will not discuss here. In particular, they are essential to realize deep brains as Volkoff-Okulov states. So that part I will not discuss. So even if you add, no matter how big fermionic contribution you add, brain or an anti-brain cannot conspire to give a de Sitter solution. Now additionally, since fluxes cannot give a 4-dimensional de Sitter, any combination of fluxes, brains and anti-brains cannot conspire to give us a 4-dimensional de Sitter solution. With or without the fermionic terms. The question is, all is not lost because we can always look for theories in which the tension of is less than 0. So question is that this can of course change our result. So do such objects exist in string theory? And the answer is of course yes, and they are called the orientifold planes, and the orientifold planes are exactly the ones which has negative torsion. And the big lore of theory was that after KKLT solution came up, but KKLT explicitly put an anti-brane, people soon realized that maybe it's the orientifold plane which does that. It cannot be the anti-brane. Anti-brane cannot uplift. So it must be the orientifold plane which is doing it. So what are orientifold planes? So many of you know it very, very well. I'll just tell you briefly. They are just like E-branes except they are non-dynamical perturbatively. Non-perturbatively they have become dynamical. They can start moving non-perturbatively. But perturbatively they are dynamical, non-dynamical objects. They carry charge where they have negative tension. For example, if you have an orientifold 7 plane, as you know, if you study perturbative string theory, it's a static object. However, non-perturbatively, orientifold plane can split into branes, 7 branes and PQ7 branes, and they can move. So non-perturbatively things are different, but perturbatively they are static stable objects. Now between two O planes, the dynamics is governed by Klein-Bottle or OBS state, and in other words, orientifold is just like an orbifold operation, creating a Z2 fixed point like that. So orientifolding is just like orbifold, except that these orbifold points carry extra charges, and these charges are the Ramon charges of the theory. Now, the energy momentum tensor, now you work out the energy momentum tensor, and it's very easy to work it out, and you get an answer which looks like that. As expected, come with a positive sign. And clearly T mu mu is greater than T mm. In this thing, it's very easy to see. So that means, at face value, it looks like we have just achieved what we wanted. T mu mu is greater than T mm, because if you plug this in, everything is positive definite, and this quantity can be bigger than this quantity. So orientifold plane should be able to uplift. The question is that true? It turns out the answer is unfortunately no. This is where we had an argument, a lot of people. The only person who agreed with us was one Mallasina, who finally we chatted with him for a long time on this one. The answer turns out to be not, actually that's not true. Although at face value it seems like it can do that, it's not doing the job because of some very interesting reason. It turns out that in the presence of an orientifold plane, we cannot just have an orientifold plane in a theory, just like that. Orientifold plane, at least in the type of compactification that we study, also known as the Giddings-Kochnu-Koczynski or the GKP construction, the theory, in the presence of, we have all kind of type 2B fluxes switched on. So we have to add the contribution of the whole package to see whether we can have a positive curvature solution. We cannot just have an orientifold 3-plane in a theory. If you switch on an orientifold 3-plane, you cannot simply say I calculate the energy momentum tensor of orientifold 3-plane. As soon as you switch on an orientifold 3-plane, it also switches on the surrounding Ramon charges of that object. It curves the surrounding background. So you have to take all of these into account and then calculate the energy momentum tensor of the theory and see whether you can satisfy the trace of the energy momentum tensor in 4 dimensions greater than that. Now, if you do such a thing, then the 4-dimensional curvature turns out to be not so simple as this guy, but it's a combination of all kind of things which contains the 3-form fluxes, the 4-form should be 5-form. Yeah, 5-form fluxes, and the difference between the energy momentum tensor of the two pieces. where by definition this one is the combination of the NS and RR three-form fluxes, F5 is the 5-form, and tau is the tau which appears over here is the axion dilaton of the theory. Note also that the right hand side of this thing should also be independent of all the internal direction. That means we could study this configuration at any point in the internal space because we are computing the energy momentum tensor in the 4 dimension. Now, if you go away from the orientifold point, one can easily see that even though this quantity is greater than 0, this whole quantity is always less than 0. You can plug that in and check for any kind of background. This quantity for any given particular solution which satisfies the equation of motion, this quantity is never greater than 0. So that means away from the orientifold point, it's not possible to get a 4-dimensional de Sitter vacuum. Question is, what happens at the fixed point? Or if we use a warped compactification, maybe we can change the conclusion using these two ingredients. So first let's study the warped compactification. Warped compactification is given by exactly the same metric I talked about, except that it has some coefficient in front of it. So warp compactification is defined by compactification in which the coefficient of the 4-dimensional piece has a piece which depends upon the internal coordinate. Now plug this in, warp compactification in the previous equation, and we get a consistency condition which looks like that. Now we have made an assumption that the internal space has no singularity. In the absence of any singularity of the internal space, the solution looks like that. This quantity is the volume of a 4-dimensional space, is positive definite. This quantity is the so-called I6, which appears for background fluxes. It turns out that this is also positive definite. And this quantity is a combination of rings and the planes. And similarly, V6 is the volume of the internal space. Now it turns out that R4 is only greater than 0 if and only if Tmm minus T mu is less than 0. Under this condition, you can get about. You want this to be positive definite. To be this positive, this quantity is positive, this cannot work. So all of these, this can only be positive if this quantity is less than 0. Now, away from the fixed point, we showed that this is not possible. If we delocalize the brane again, this is not possible because for the brane, this quantity is always greater than 0. So the only way this could change is if something drastic happens at the orientifold point. The question is, can this be possible? Well, one way would be to delocalize the orientifold plane, but nobody knows what is the meaning of the word delocalizing an orientifold plane. So the question is, are there other ways? And this is where we find that the classical description cannot explain what is going on, so we have to go to a more elaborate description to understand the behavior of the theory right at the orientifold point, and this is where we analyze the theory using M theory. So what is M theory? M theory is described as the theory of 11-dimensional theory, which captures the captures all supergravity in this particular way, and the law is that M theory by definition can explain all theory, or as they say, one ring to rule them all. Now it turns out that in M theory, the one advantage of studying everything in M theory is that you can package all of these, the 3-form fluxes, that dilaton and all these things in one particular 4-form additionally, the orientifold planes of type 2B theory become smooth spaces in M theory. For example, if you have a orientifold 5 plane in type 2B theory, this will become an orientifold space in M theory, which gets smoothed out by certain thing called twisted center states in M theory. If you have an orientifold 7 plane in type 2B theory, in M theory it becomes a Hitchin space, which is a smooth space. If you have an orientifold 3 plane in type 2B theory, it becomes certain kind of orientifold fixed point in M theory, which can also be smoothed by certain twisted center states. So all the orientifold planes, points in M theory or type 2B theory become smooth spaces in M theory. So with the O planes, fluxes and branes, the precise condition from M theory takes the following form. So if you plug in everything, branes and all, the orientifold and fluxes and everything, I get a consistency condition which looks like that, where this quantity is the 4-form fluxes. This is the 4-dimensional cosmological constant. This is the square of the warp factor. This is the metric. And this is the brane and an anti-brane, which become a 2-brane or an anti-2-brane in M. And you notice that all information of the orientifold plane does not appear in this, because all the information of the orientifold plane in M theory becomes smooth spaces. So all you see in M theory are the brane singularities. You see a smooth warp factor, and you see the fluxes. So this is the condition you get from M theory. And now you see, now the condition is that you want to get a 4-dimensional positive curvature solution. Now this is impossible in this equation, because this quantity is a square of a number, so it's positive. This quantity is a number of brane, it cannot be negative. This quantity is square, so everything is plus. So it's impossible to get a plus over here. So a positive cosmological solution, as you can see, it's impossible to get in this case. So that captures everything you need to know about theory. That you see, it's very easy to get a 0 solution, because if the fluxes are 0, lambda is 0, or a negative solution. If this is negative, with the presence of positive fluxes and branes, you can always get a negative solution. So this should remind you of the condition somewhat originally found by Becker and Becker on M theory or like that. But I am doing it in a more elaborate setup, assuming that there is a solution of that. So this is what captures the whole essence of two-derivative gravity. That no matter what you add in a two-derivative gravity, you can get a lambda equal to 0, lambda less than 0 solution, but never a lambda positive. So under what conditions? So when we got this equation, it was completely clear to us why it's so difficult for nature to, the string theory, to get it. Because you cannot manipulate this equation to get. The only way is to add a negative term in this theory. To add a term in this theory which is completely negative definite. Then only you can get a negative lambda solution for this theory. Now this is exactly what I said. Since all terms are positive definite, lambda can never be positive and satisfy that one constraint. So here is the summary. Neither d-brane nor anti-d-brane with arbitrary word volume fluxes in the presence of active fluxes and scalar field result in a positive curvature in 4 dimension. Moreover, even O planes with negative tension do not give rise to positive curvature solution. Therefore, we conclude that in two-derivative gravity theory arising from string theory, there is no positive curvature solution. So can we somehow change this conclusion, and we have to show that how KKLT solution is a consistent solution, because there should be something in the KKLT solution which has overcome all of these things. Well, as indeed suggested by Hawking, in gravity, conclusion can be drastically changed once quantum corrections are added. So you add a quantum correction, And it changes this consistency condition if you stare at it carefully. This was all positive definite solution. So if you add a quantum correction, it changes in a very clear way. It changes in this following way. The quantum correction adds up like that. It keeps the positive pieces like that, and it adds something which looks like that. And now, it turns out that in 4-dimensional de Sitter, it's only possible if the quantum pieces sum up to some negative definite value. For example, in this picture, you see if this whole quantity is a completely negative definite quantity, then it's possible to have a lambda greater than this.
Sorry, what's this C?
I haven't written what are C. These are the pieces associated with quantum corrections.
So is it up to the portrait?
R to the power 4 and higher, all higher terms. And so the conclusion here is that as you stare at it over here, this whole quantity should be negative definite, and this quantity looks like C AA plus C MM minus C mu mu has to be less than 0. This is the quantum piece. Okay, and we put everything together. On that side, it looks like C mu mu is greater than C mm plus C A, which is exactly should remind you of T mu mu greater than T mm, but now they are measured for the quantum case.
Why are these 8-dimensional integrals? Did I miss something on there?
Okay, that's a good question. This was originally showed by Becker and Becker that if you have type 2B on a 6-dimensional manifold, this, if you take it to M theory, it's M theory on an 8-fold. Now 8-fold is written as a T2 5 over this one, and in the limit when the T2 shrinks to 0 size, we get a type 2B theory. So M theory on a T2 fibered over a 6 manifold, in the limit when the torus shrinks to 0 size, you get a type 2B on. This looks like contradictory because M theory on an 8-fold should give us a 2 plus 1 dimensional theory, not a 3 plus 1 theory. But the subtlety was explaining in their paper, it's a very interesting thing. The whole process is the condition that the torus has to shrink to 0 size. Not finite size, but completely 0 size. And you can see why this is the case. Because if I have an M theory on a torus, and I'll shrink the torus is S1 cross S1, and I'll shrink 1 by 1. So if I shrink S1 to 0, I get a type 2A theory. And now I shrink another S1 to be 0. Then I get a, as soon as I start shrinking to 0, as soon as I cross alpha prime, it goes to its other direction, it becomes a T-duality, so it T-dualized to it. It's a very interesting thing. It's shown originally some consequence of that. So that's the reason why this 8 integral is coming over here. And this relationship is exactly the condition that this quantity has to be negative definite. In other words, this mu mu term has to be greater than that, which is exactly the thing which we had for classical. So, as the quantum corrections or the non-perturbative correction, the energy momentum tensor and on the 4 dimension has to be greater than the energy momentum tensor. So, if you can show that the quantum pieces are all positive definiting, now note something. It has to be an infinite sum of all quantum, a whole set of quantum tower. All the non-perturbative correction in M theory, they should sum up to a negative definite quantity, and then under that condition it's possible. If you compute only 100 quantum pieces and you turn out that this is negative definite, but 101 quantum piece is positive definite and the whole thing is positive definite, you will not get a positive curvature solution in string theory. So our prediction is that you need to know the whole corrections in M theory to predict a situation like that. And the quantum pieces, the total sum of all quantum pieces has to sum up to a negative definite quantity to give you a positive curvature solution. This is why getting a de Sitter solution is so hard in string theory. But this is our final conclusion, and it will surely make Einstein happy. So the conclusion is the following, that in a two-derivative gravity, it's impossible to get a body de Sitter vector using any combination of branes and brane classes or planes. Conclusion can be changed once quantum corrections are included. However, if quantum correction all sum up to some positive definite value, then again no de Sitter solution will be possible in string theory. I know that SAB has a way to show consistency of what as well. Since at an instant on SAB city. But we couldn't find any other way out of this thing. So the KKLT solution that people have, well, these quantum correction appear from string and brane instantons in string theory. Now we believe that precisely this quantum correction are responsible in some way to realize the famous KKLT solution in tactical string. So I think the KKLT solution is correct because somehow in KKLT solution there are ingredients in the theory. You should not consider that KKLT solution is just uplifting using anti-brane. That's not the right way to understand KKLT solution. The KKLT solution should be understood as a combination of O planes and anti-branes. In KKLT solution, the anti-branes make supersymmetry but does not uplift. The O planes and the correction, they actually are responsible for uplifting. And I think they are the ones which are responsible in some way to realize that. So hopefully I was able to convey the main points of our work. We are presently working on the application of this. And since I am from Montreal, merci beaucoup.
More questions? So a lot of the analysis you did today, especially some of the numerology, seemed very special to 4 dimensions.
Yes.
What if I don't care about our universe and I wanted to find some
I think it's
other
possible.
dimensional?
Yeah, that would be possible.
But are there any examples?
I don't know, we haven't analyzed that. Only 4D.
That'd be, you could have like a 6-dimensional series or something.
Right.
Any other questions?
I've forgotten the details of the KKLT thing. I mean, but you were just now saying that you suspect that this is what's going on. So,
Okay, so let me explain to you what KKLT solution is. So what KKLT did, they did a remarkable job of putting things together to get a positive cosmological solution. So they used fluxes, anti-branes, and O-planes to study. So the way they did it is that they assume that the space-time is divided into 2 pieces. One is this 4-dimensional piece, and the other is some 6-dimensional piece. Now, so this is how our space-time will look at, and this should be de Sitter solution, and this should be some internal space. Now note something, that if the internal space is not compact, if it is non-compact, then it will be difficult to get a finite Newton constant in one dimension. The Newton constant will blow up. So the only possible way to get a finite Newton constant, unless of course you use the Randall-Sundrum type of scenario, it will not be possible to get it. So you have to have a compact. their first criteria. Now, they also know that the four-dimensional theory has to break supersymmetry. So they have to add a term in this theory that breaks supersymmetry. So they added, the simplest way to break supersymmetry could be fluxes of brane. In the original paper, they added an anti-brane. But as soon as you add the anti-brane in this theory, which will be a point in this thing, you can easily see that Gauss law is valid. Because in a compact space, you cannot put charge in a compact space. The Gauss law is violated because this charge created by an anti-brane has no place to escape. Since it's covered the space-time, it cannot escape along the space-time direction. So it has to escape in the internal direction. But there is no way they can escape the internal direction because the internal space is compact. So now they have to eat up that charge. So as soon as they added this, they have to eat up charge. The only way to eat up charge is either put fluxes over here or O-flakes. So they put both. They put fluxes over here. Now why do they put fluxes? Because one can check that the fluxes create an anomaly cancellation condition. They actually have enough power to cancel the charge to satisfy the Gauss law. Now, as soon as they added fluxes and an anti-brane, they had to realize the fact that due to Dine-Seiberg-Ranaway problem, this internal space has a lot of cycles inside it. But as Dine and Seiberg pointed out, if you just create a compact space like that, if you leave it like that, the compact space will decompactify. But they cannot let it decompactify because as soon as it decompactify, you get 0 Newton constant in 4 dimensions. So they have to somehow. So putting a fluxes and putting anti-brane is not enough. But one good thing the fluxes will immediately do is that it will stabilize all the complex structure of this cycle. But the cycle has scalar modular. In other words, the cycle has size. The size grow. So they have to do something to keep the size of the space intact. So now it becomes more complicated. So they have to figure out a way to keep the size of these cycles to be finite. Otherwise, they will just blow up. Now, one immediate possibility is to add brane instanton. The wrap instanton around the cycle. So if you have a cycle like that, and if you wrap some instanton, the instanton will tend to, the cycle will tend to grow because of Dine-Seiberg, and the instanton will tend to shrink because of their energy momentum tensor like that. So there will be a stability delay. So they added instanton in this theory, which are basically a 3-brane instanton in this theory. And then they came down. But as soon as you add instanton in the theory generates new higher derivative corrections in the theory because instanton corrections. And they claim that the deciduous solution is got by under norms. Now we reanalyzed the whole thing and we realized that these correction by instanton and all the non-perturbative thing are in fact the essential point to realize that. So this whole construction, which is not simple, which is I think it's a remarkable way they put everything together. It's called the KKLT. That paradigm is called.
So in a slightly indirect way, they have invoked higher derivative stuff.
The whole point in type 2B is that if you add something, you add a lot of things to balance the whole thing. Because if you require an internal compact space, then you stabilize the whole thing.
Instantly is kind of non-perturbative effects.
Huh?
Instantly non-perturbative effects, but hard to kill some sensitive perturbative effects.
No, instanton can also create higher derivative terms, as was shown by Green and Gackward and other people, that instanton can also lead to higher derivative corrections in the theory. They are the curvature corrections. Instanton can lead to r to the power of 4 and higher.
But in original KKLT paper, they just introduced the instantaneous superpotential form and they didn't involve in high derivative terms.
No, they did not.
So you're supposed to explain this instant effect
Yeah,
by
but,
the high derivative effect.
More modern understanding is Original paper was the claim is that anti-brain is used to uplift. I don't think that's quite correct. Everybody in the field now realizes that even Renata said this. Anti-brain cannot do the job. It has to be some combination of all of this. But definitely there exists a solution. Whether a solution is realizable or not and under the satisfied conditions satisfied is to be checked.
So basically, you want to find the positive cosmology constant in the string theory. But I have a question: is that necessary? Because we can explain the dark energy as a scalar field with non-zero value, but its mass is very small, so it changes very very slowly. So. And it can be this scenario can replace the cosmology constant.
Yeah, that's a good question. One thing I know, well, I'm not expert on all this. I cannot give you an answer. Maybe somebody else knows.
So far, lambda CDM is still the best model.
The first no.
Yeah, according to
HET
what
constant.
Robert told me, I can only quote what Robert told me that
But I think
it's the best case scenario is that particular thing, but the end point of the influence, so it's you start with the inflationary paradigm and come to the end point of the inflationary paradigm. At the end point of when the system is going through an inflationary paradigm, you don't require a de-Sitter solution. But the end point of the inflationary paradigm, which is in the hybrid inflation, which becomes at the end of the waterfall stage. At that particular point, when you come to the end of the inflationary paradigm, at that point you require a positive cosmological solution, not at an intermediate stage. So if there exists a state like that in the theory, and if string theory is the right theory to explain, you should be able to explain how such a positive cosmological solution can come out at least. If string theory shows that there cannot be any positive cosmology, that's a different issue altogether. But at least they should be able to show at any particular stage of the evolution of the universe, there should be one positive cosmological solution.
Any other questions? Thank you, Keshav.